All right, so welcome back. We are in section 5, chapter 2, and the topic is something we alluded to at the very end of the last video, which is the idea of a special integrating factor. And let's go ahead and unpack the scenario. So you have a differential equation that appears to be an exact differential equation, right? Except when you go to test it, it fails its exactness test. So the question is, do we need a whole nother way of solving this differential equation, or is it possible to get this equation in exact form? In other words, is there something out there, right? Some function out there that if I multiply by that function, I can go from a non-exact equation to an exact equation. All right. So that's the idea. If you can, then we're going to label this U, all right? This is what we label the special integrating factor, right? So if it can be done, if it can be manipulated from non-exact to exact equation, then the function that does that for us is the special integrating factor. So for this section, instead of me going through a bunch of theory at first and then going to an example, what I would like to do is just get to the example very quickly and then learn the theory through the example, okay? So I'd want to highlight that we're going to come back to this little theorem after we start to unpack the example. But this exp is just the author's way of saying e to the power of, okay? So really quickly, let's just go to the example. All right, so here's our differential equation. So it appears to be in exact form to me. So hopefully it appears to be in the exact form to you. So what we do is we go through and we test. So we take the partial of m with respect to y, partial of n with respect to x, and obviously these do not equal each other. So now the question becomes, can we find a special integrating factor? Okay, can we find it? Well, let's start this way. So the idea is, again, remember, we're going to learn the theory through the example. So the idea is that if we can, so we already have the partial of m with respect to y, and we already have the partial of n with respect to x. If we set up a quotient, notice this quotient. So we're going to take the partial of m with respect to y minus the partial of n with respect to x. So that's 1 minus 2x minus 1. And whatever that outcome is, we're going to divide it by n. Okay, so let's go ahead and just label. All right, so this is m, this is n. Okay, now I agree with you. Well, how does that work? Why does that work? What's happening here? Well, let's see if we can start to unpack that. So let's try setting this up, and let's take a look at what the result would be. All right, so I'm going to I'll write it, the partial of m with respect to y minus the partial of n with respect to x divided by n. Okay, so that would be 1 minus 2xy minus 1 divided by x squared y minus x. Okay, so you can see where I'm just going to draw you some arrows that are going to disappear. All right, so that's what the formula told us to do. Now let's see what the result would be, okay? So let's simplify this a little bit. All right, well, we can drop those parentheses here, right? We could drop these parentheses, just we got to make sure we distribute that negative symbol. So this is going to be negative 2xy. And then, of course, this one is going to cancel. No, let me see here. We have negative 1. Oh, no, so that is going to be end up being 2, isn't it? Yeah. So we're going to have 1 minus a negative, so that's 1 plus 2. All right, so that numerator is going to simplify to negative 2xy plus 2 over x squared y minus x. Okay, now, so this is where this is us applying the formula that we have no idea where it came from yet. But to know if this is going to work, what must happen at this point right here is we must be able to simplify this quotient such that the only variable remaining is the x variable. Let me read, right? So you start off with your exact equation, right, or proposed exact equation, and we figure out it's neither separable nor linear. We go through and compute the partials. We figure out it's not exact. So if it is not exact, we use this quotient or this quotient. We would try both. If the first one doesn't work, we go with the other one. And here's, again, what must the end result be? Well, it says, so if you try this quotient, then what's left, this must only be a function of just x. So right now, let's see if we can simplify this a little bit further, and then we'll see if we can discuss why must it be only a function of x. All right, well, I think you'll agree with me. I can, let's see, I can factor out, you kind of have to be savvy here. I can factor out a 2 from that numerator. And if I did, I would be left with, let's see, negative xy. Negative xy. Plus 1. No, right? Yeah, so plus 1. All right. Now, the only way this is going to work is let's take a look at this denominator. Well, let's just answer the question. What could I factor out of here? Well, I could factor out an x, or I could factor out a negative x, right? Both terms have an x variable. Now, I'm going to choose to factor out the negative x. And the reasoning, quite simply, is because you would be left with, if you took away one x, you would be left with a negative xy. And if you factor out a negative x, you would be left with a plus 1. Right? So let's think about it. If you take negative x times 1, you get negative x. If you take negative x times negative xy, negative times a negative is a positive, so you get x squared y. So why choose the negative x over the positive x? Because look how these factors cancel. In other words, what is the factor with the y variable, right? Remember, it said must only be a function of just x. In other words, the only variable that is remaining must be x. So the idea of that allows us to, let's go ahead and write what's left at that point. So the idea, let's try not taking the rest of that. So the idea is that as soon as you get done with that factoring and canceling, the only thing that you're left with is 2 over negative x, or I'll just write it as negative 2 over x. Now, because this is only a function of x, then this formula worked. Let's assume for just a second that you kept trying to factor and you just couldn't get it. There was always a y variable left. So, okay, so maybe we abandon that little formula and we try this formula, which is now it's just the partial of n with respect to the x minus the partial of m with respect to y. So in that case, it would just be 2x y minus 1 minus 1. And now, instead of dividing by n, we would divide by m. So you see how you would go through the same process again, simplifying, but now, if you chose this formula, you would have to be, whatever you're left with must be a function of y. Okay? Okay, so clearly this worked. We are left with only a function of x, but we still don't know why must it only be a function of x, and nor do we understand how that any of that gets us to this special factor, integrating factor. Well, let's go back a page and let's look at our definition of the special integrating factor. Okay? Now, notice what I'm trying to simplify this for you if you'll follow me for a second. Notice that these are our definitions of the special integrating factor. Okay? That we're going to have we're going to e to the integral of something, right? With respect to x, or e to the integral of something with respect to y. Now notice that what they have for the something is exactly the formula on the previous page, right? So now, do you see that if you have to plug in something here and integrate with respect to x, then you must have only a function of x. If that doesn't quite connect yet, let me come over here. So the idea is that whatever we have here is going to be inserted right here. And clearly, if you're going to integrate with respect to x, that's why you can only have an x variable, right? The integrand must only have the variable x. So that's why that condition was stated. So good. So let's go ahead but the good news is that is how we compute the special integrating factor. Now, if you really wanted to unpack this special where this all came from, you would have to go back to and I promise you I won't, but you would have to go back to that linear differential equation back in 2.2, right? That's where you have the dy dx, and then you had your p of x, y is equal to q of x. You would have to go back to this original linear differential equation, and then you can start to unpack where what you would end up doing is distributing a dx, separating, and then setting equal to 0, dividing out a dx. But that is but with your permission, and I don't think you'll mind too much, how about you just accept that this formula works? Okay? I offer it to you without proof and without further explanation. And that I offer you the fact that the special integrating factor is defined as such. So if you will take me at my word, then we can proceed to just substitute negative 2 over x in here to get our integrating factor. So let's go ahead and do that. So that would be e to the integral of negative 2 over x dx, right? And let's go ahead and figure out what that ends up becoming. So that's just well, I mean, I won't spend a whole lot of time. You can just write that as negative 2x to the negative 1, right? This is what you're actually integrating. If you take out that, if you pull out that negative 2, you're just integrating x to the negative 1 with respect to x, which is just ln. Right, so what we end up with is e, let's see here, maybe, it's going to be e to the negative 2 ln x is what we're going to have at that point. So e to the negative 2 ln of x. All right. So that is, so at this stage, we're done with that integrating. And well, remember that this is the thing that we're going to multiply, we're going to distribute to our original equation so that we can make it exact. So my suggestion to you is to fall in love with manipulating ln's and log properties, because what I'm going to do, I want to make things easy. So I'm going to take this negative 2 and bring it inside the ln, right? Just the reverse of your log properties, so that I can take e to the ln. So that's e to the ln of x to the negative 2. And of course, anytime you have e to the ln, that's going to cancel out. So you're just left with e to the ln equals, just going to equal 1. So you're just left with x to the negative 2. All right. So there it is. There's your special integrating factor. So let's go ahead and let's distribute this x to the negative 2 to our original equation, right? And let's rewrite what that would look like. So now our equation looks like the following. So now we have, let's see here, 2 plus yx to the negative 2 dx plus y, that's going to be, let's see, what do we got? Negative x times x to the power 1 times x to the negative 2. So that's just going to be minus x to the negative 1. Okay. dy equals 0. Okay. Let me, if you don't mind, entertain yourself for just a second. I'm going to make sure I distributed this correctly. So 2 plus y x to the negative 2, y minus x to the negative 1. Yes, okay. So now here's your new differential equation after distributing by that special integrating factor. And now you would go back and you would retest for exactness, right? That way you made sure that you did everything correctly. In this case, it will work. Okay, I mean, you can go through but in this particular case, once you take that partial, forgive me, partial of n with respect to y, and that partial of n, new n with respect to x, they will equal each other. Before they did not, but now they will. So now you do have an exact equation, and you can proceed, right? You can proceed to use the techniques from the previous video. Now, what I'm going to do is I'm not going to, like from here, this we could, you know, once we start here, this is not a 2.5 topic anymore, right? This is a section 2.4 topic. So what I'll do is I'll just go ahead and give you the solution, right? And if you happen to have any trouble, you can always reach out to me during, you know, office hours if you have any trouble arriving at this. But what you'll end up with is g of y is equal to y squared over 2. When you go back and plug that in, this is the result. Okay. Now, so again, so this is the final product here, the final result of our solution. The only thing that has been lost along the way, and this is where you have to be careful. So notice that x, so first let's establish x to the power of negative 2 is equal to 1 over x squared, right? In this case, x cannot be 0, right? You'll be dividing by 0. So what's happened along the way, all right, is you have lost a solution. This is not, what I'm attempting to tell you right now is not as important to your test and your test questions and things of this nature. It's more of structurally, when you start distributing functions, you have to be careful for what's called extraneous solutions, right? Where you can accidentally lose solutions that were there, or you can gain solutions that were not there. In this case, we actually lost a solution. If you were to look, you would also have to, if you were to look at this, you would assume, well, x cannot be negative, x cannot be 0, right? If you were to look at your answer, this part right here, you would say, well, x cannot equal 0. That's actually not true. It's only because of our distributing x to the negative 2 that that caused us to lose a solution. So, you know, this is, you know, plus x equals 0. So we want to make sure, I just want to make sure you understand that 0 is still within the domain here. But x equals 0 was lost. Okay, so let's go ahead and stop here. We'll start back up with the next video. Hopefully you have a decent, you know, again, I know that I only gave it a cursory overview, but what I want to do in the next video, when you get back, is I want to show you how I learned this method back when I was in college. And in other words, when this doesn't work and this doesn't work, you can't get this as a function of x, you can't get this as a function of y, what can you do? So when we get back, I'm going to teach you, do one more problem for this section using what we call the x to the n, y to the m method. And again, I never learned any of this stuff when I went through college. We solved every single exact differential equation by the method that I'm going to show you in the next video. But I will see you there.